Hello, everyone. My name is Mike Lawless, Business Development Manager, Cheminformatics Solutions, and on behalf of Simulations Plus, I welcome everyone to today's webinar, which will discuss new features in ADMET Predictor 8. An opportunity to ask questions will follow the presentation. You may either send your questions using the questions pane on your control panel, or you may ask your questions directly using the hand-raising icon. If you're using a telephone to listen to the call, please be sure to enter the unique audio PIN displayed when you join the call. When you enter your audio PIN, this enables us to unmute your line so that you can be heard. This webinar is being recorded for playback at our website, www.simulations-plus.com. Also, upon request, the presentation slides can be made available to be shared with colleagues. So let's go ahead and start the webinar now. So this first slide kind of tells it all. We've taken ADMET Predictor 7.2 and really redeveloped the interface and added medicinal chemistry tools also to it from our MedChem Studio product. So your user experience has been redefined. Just want to first acknowledge the Cheminformatics team here at Simulations Plus, who's done a lot of great work over the last year working on this ADMET Predictor 8. So I'll start with Bob Clark, our Director of Cheminformatics, who's also a panelist on this call. Robert Franskevich, Marv Waldman, David Miller, who did a lot of the porting of the code to the new system. Ola Mikos and Pankaj Daga, who joined us recently and just became a new father last week. So this is an overview of the talk. It's going to be kind of in 4 different sections. First, I'm just going to give an overview of ADMET Predictor 8. The important thing is that we still have our top-rated QSAR models as always in the program, and we've added a really nice user interface. So there's no reason to use, and then we've also incorporated molecule design tools from our MedChem Studio product. So we've combined kind of ADMET Predictor and MedChem Studio together in one interface to make it very powerful. We now have what are called star plots in ADMET Predictor 8. People that have used MedChem Studio will have seen star plots, introduced heat maps, and then also kind of rearranged the scatter and distribution plots so that they're on the main screen. And I'll show how to interact with those. Then I'll go in and discuss a hERG inhibition classification model. I'll talk about data curation and show matched molecular pair analysis to extract SAR in the data set. And then I'll just run through a slide showing the new ADMET modeler interface. And then I'm going to go into an example application of BACE1 inhibitors. I'm going to show kind of the setup of that and then take a subset of that data, generate classes, R tables, analyze show how to analyze the R groups, and then explode the products. And then in this last section, I'm just going to introduce this with slides. And the theory here is you're starting with a single initial hit, either from maybe a related project or related target. Show how you could use medicinal chemistry interface, intuition with the MedChem designer, maybe perform some library searching, which is now available in ADMET Predictor, and perform combinatorial transforms, which kind of introduces MedChem intuition, but also uses the program to make those, and then also virtual library generation. So the new graphical user interface is shown here. This is the main spreadsheet. We can create with the scatter plots. We have a dynamic link between the chart and the spreadsheet so that things that are highlighted in the spreadsheet can be highlighted in the chart and vice versa. We create heat maps. If we do a substructure query, we'll highlight the hits in the data set. So this was just a query on an aromatic carbon connected to a chlorine. This next slide shows the automated star plots. These are created right after the ADMET properties are computed, and has things for risk, physchem bio, SIP sites of substrate classification models. If a wedge is hashed, I'm not sure how easy that is to see on the yellow, but that indicates that it's out of scope. So you can see this purple one here a little bit better down in the corner. Okay, so let's start up ADMET Predictor 8.0. So with the new interface, you can simply drag a compound or an input file onto the icon and it will start the program. So this was a smile string I read in here. It has two columns. The first column is the smile string. The next column is an identifier, and then it also contains some experimental solubility data. And so you can specify what you want to use, which column you want to use as the smile string, which column you want to use as the identifier. You want a unique identifier for each molecule in the spreadsheet if possible. Then I click OK. And the first thing I want to point out are these last two columns here. So when the, let me make this a little bit bigger, dragging this down. When the program opens a file, it looks for common salts defined in a file, and will also remove smallest fragments. And it's identified these fragments in these two columns. So this column here is the original smile string from the file. So you'll notice that it's got a hydrochloric acid. So this is the hydrochloric salt, and this is the sodium salt of this compound. And I simply edited this smiles file just to demonstrate those. So if you want, you can remove these automatically with the program. Okay, so we can also undisplay columns. So if I do a right click on a particular column, I can undisplay that. I can also go up to the View menu and go to Arrange Columns. This is something I use quite often. I usually use the shortcut Control-Alt-V. That'll bring up this dialog box, and this allows us to select attributes over on the displayed column and remove them from the display. With ADMET Predictor 8, we're going to be displaying a lot of properties, and it's very important to be able to manipulate these columns and rows so that you can get the most information and simplify the data. Okay, so now we've got a solubility column and our structure column. The next thing I'm going to do is calculate ADMET properties. I can click on this icon here to bring up the Calculate ADMET Properties dialog box. We can customize the properties if we want. So we could uncheck all, and let's say we just wanted to compute the descriptor aryl hydroxyl OHs. We could click OK, and then just that column would be displayed. I'm going to display all of them, so I just click all, and then we can also change the pH here. So click Calculate. What happens here is that it goes out and it calculates all the descriptors and then uses those descriptors to calculate the model properties. So here is our star plots. We can just kind of page down through here. So the first one is for the risk columns, or risk, and so this is for the ADMET risk, the absorption risk, SIP risk, mute risk, and tox risk. And so the length of these are proportional to the data set, or the range for this particular data set, and the longer, obviously, the higher the value. If we go over to the PCB, you can see these properties. Now note that the solubility, we take the log of that column. If I right-click here, I can modify this plot. So here we have the fields, or the attributes for this particular plot. We could remove some of those. We could select some over here and add them over to here. And then down here at the bottom, this is where you specify each one of the attributes selected over here. You can specify the color, the minimum and maximum values, and then you can take a log scale of those also. So it's versatile. There's also an ASCII text file that you can modify yourself to remove properties or add other properties for these automated star plots. Then moving on to some of the phys-chem properties, if you double-click in a particular gray cell, it will bring up another window. In this case, it brings up the pKa microstates for this molecule. This is biotin. You can also display the distribution of microstates, the fraction ionized versus pH, and then loop through the various plots here. If we go down and double-click on a particular image here, it will bring up MedChem Designer. From MedChem Designer, we can calculate metabolites. So I click the metabolite button. For this compound, it produces the metabolites similar to ADMET Predictor 7.2, but what's nice in this next version is that it also shows the clearance, the intrinsic clearance for this, and it's scaled up to their expression levels in the liver, and then shows the individual clearances to make all of these metabolites. Along with the those predictions, we get the percent metabolite formed for each of the metabolites. So this is the major metabolite, it's 84%, but this is a very low clearance, so not much of this would really be produced anyway. So let's exit that. I'm going to save those changes. You can also select a number of compounds and generate metabolites in batch. So I did a right-click, generate metabolites. That brings up this dialog box. I can select the enzymes. Here I've only got the 5 major enzymes selected. I could write the input file or the input molecule, the parent molecule, to the output file. I'm going to display the results in a new table. And I'm also going to click the advance. So the previous example I showed didn't have intermediates, but you can choose to display those or not display those. In batch mode, I'm going to choose not to display those and then calculate those. So it goes out and makes all those predictions and then brings up ADMET Predictor in a new window with the metabolites. So if we focus on these first 4 or first 5 rows, this is for cocaine, this is the 4 predicted metabolites for it, and then we also have the percent yield for each one of these. So if we go down a little bit further, this was the example I showed in MedChem Designer, and so we have 84% for that one particular compound. Okay, so the next thing I want to do is go into ADMET Predictor and to show the structure query tool. That's under Edit, Query by Structure Property. It brings up this dialog box. There's also a query wizard here, which allows you to query for different properties or text values. Let's say you want to just select compounds with a log P between 1 and 3. You could use this query wizard. I'm going to again bring up MedChem Designer and sketch in a chlorophenyl group. So I add a bond here and then the chlorine, and then I transfer this back over. So now it shows the structure of the query molecule. We could also show the SMERC string for that. We click OK, and it's highlighted 15 compounds. Now, if we want to kind of take all these and show them together, we can move them up to the top. And so I'll move those up to the top and highlight those so you can see that all these are highlighted as such. We can go into this distribution plot, and if we click on this icon in the upper left-hand corner, it will show the what we want to plot here. By default, everything's in alphabetical order. We can change this. If we push this button, it will display these in the group by the various modules. So first comes the phys-chem bio properties, the metabolite properties, or metabolite module, and then finally the toxicity and the descriptors. So I want to select log D here. I just click OK, and that creates the distribution plot for log D. Now I can also go to a 2-color mode. If I click there, it will show the chlorophenyl compounds in red here, and this is using the secondary axis over here. So it's kind of a percent of each different category, and I can change that from the default using a second value. And then click OK. So now this is relative to the overall data set, and shows obviously there's fewer chlorophenols in this, but you can see that obviously they have a higher log D than the other compounds. These charts are dockable, so I'm going to bring this out and take a look at it here. If we right-click, there's various options we can use on the background. For example, we can change from circles to squares, change the point size, background color, so a lot of options in there. I'm going to plot the experimental solubility. I'm going to logify that, and then I'm also going to select the our model values over here. So I go down to the S plus SW, I'll logify that plot, and then click OK. So now we've plotted the log of the observed values versus log of the predicted values. We can create a regression line simply by clicking on this icon here. Gives you the correlation coefficient of 0.8, and then shows the slope intercept, and then the root mean square error and the mean absolute error relative to this best fit line. The root mean square listed here are relative to the two values here. Now, if we want to highlight the structures in the plot that are highlighted in the spreadsheet, we click this button here, and that essentially moves what's selected in the spreadsheet over to the chart. And then we can hover over a particular point in this, and it'll show that these are all the chlorophenyl compounds here. Now, we also have a zoom capability on this, so we can kind of highlight a certain area, and it'll recreate or define these axes to kind of look specifically in those areas. We can also highlight a group of compounds in here and then shove them over the spreadsheet, and it highlights those compounds in the spreadsheet. Then to redock this, we can drag it over by its header and move it over in here. There's also a button called View Dock into Main Chart Window, so it'll go over and dock those into there. Now let's move back into the slides and discuss hERG inhibition model. So I just want to first point out that ADMET Predictor already has two really good hERG models. The hERG filter is the classification model to predict hERG binding. The cutoff is an IC50 of 10. So if it's above 10, it's a non-blocker, and if it's below 10, it's a blocker. We also have a model that predicts IC50. So I just wanted to point that out. What I'm going to do is kind of work through an example of curating a literature data set of hERG blockers. This is a recent publication from Journal of Chemical Information and Modeling, and it was published in 2016, very recently, from these authors. I believe they're from the U.S. Department of Defense. So they were kind enough to provide their training and test sets in the supplemental information, and so I could download that and just look at that. So in this example, we're going to do some data curation. We're going to read the files in, standardize the compounds, do some duplicate checking, and then finally look at some matched molecular pair analysis. And then for A&E model building, I'm just going to go through some slides for that. All right, so let's go back here, start up ADMET Predictor again. And then I'm going to read in the first data set here. So I go File, Open, and then navigate to my data set. So this is the training set of non-blockers. So the supplemental information had each one of the 4 sets separated in different tabs. When I click OK on it, now this format had the ID first and the smile second in the second column. And so the program's smart enough to realize that, so I just click OK. So it brings up some warning messages. So it's always a good idea to look at the warning messages. So there's one compound with an iodine in an odd valence state. So we need to look at that particular compound. Then these final 4, one of them contains a silicon atom, a couple others contain mercury, and then a final one contains selenium. And these are non-organic chemistry or chemicals, atoms, and they're not parameterized within ADMET Predictor, so we need to remove those. So if I sort on this AP warnings column, I see these first 5 molecules that have the warnings, and this is just an odd state of iodine. So I'm just going to remove that. Again, I'll need to remove the mercury, silicon, and selenium. I can just go up to the edit button or the edit pull-down menu and select delete to remove those compounds from the data set. Next thing I'm going to do is add an attribute. So this is going to specify the hERG inhibition, the experimental data. So I'm going to take the attribute name, call it blockers. So it's kind of a question. Is this compound a hERG blocker? The answer to all these are no, according to the publication. So it adds this column right in here. So the next thing I'm going to do is import the blockers. And so I'm going to go into File, Import Compound Structures. Now that's something that wasn't available in ADMET Predictor 7.2. So I double click on the blockers. This is in a similar format. Click OK. Now this says skip compounds with duplicate names. So that's an option if you're confident in the data set and you know that there's some duplicate names and their duplicate structures. Maybe you might not want to read those in. In this case, I'm not sure exactly what I'm reading in, so I'm not going to skip any of those. So it imports all those molecules. Note that it added an attribute called AP import, and for the ones I just imported, it assigned a value of 1. If I did a second import, it would assign those a value of 2. So we know what compounds were imported and in what order. So now that these are selected, I'm going to add their attribute. It selects them automatically and then gives us the details down here. I'm going to add another compound attribute. This time I'm only going to use the selected rows. Click OK. Constant value, and if the attribute's already there, it just modifies that for these new compounds, and I'm just going to type yes because these are blockers, and then click OK, and it's added that particular field. So now I'm going to just go up here and undisplay some of these columns, again go into View, Arrange Columns, and throw out this one, and then these bottom 4, let's move those over. So now we have the hERG blocker. Now I'm going to kind of allow visualization of that. So I'm going to create a heat map. And then it's always a good idea to take a look at this and sort the heat map. So this is labeled the non-blockers red, or colored them red. Typically, you don't want hERG inhibition, so I would prefer those to be green. The way to do that is simply go in and set the direction to descending. So now it's descending or a different order. You see the red ones are now highlighted, or the yeses are highlighted in red. Okay, so the next thing we need to do is standardize some of the structures, and there's different options under the chemistry menu. We're going to standardize the functional groups first, and what this would do is maybe if it has a nitro group represented as a nitrogen with double bonds to both oxygens, it would convert that to a nitrogen with a single bond to one oxygen and a double bond with the other oxygen, nitrogen would have a plus charge and the oxygen would have a negative charge, the one with the single bond. So I click OK, and none of those were modified. So those are all, these are all in the standard form that we'd like for ADMET Predictor. The next thing I'm going to go do is neutralize all of the compounds, and I'll just click OK. And so that's added a previous structure field. So again, let's sort on that, scroll up to the top, and I can again widen this column a little bit to make it easier to see these structures. Similarly for these compounds. So you'll notice that the structures I read in, protonatable amines were protonated with a hydrogen, so I have a plus charge, and then the neutralization just simply took that off. There's a couple negatively charged groups, so it just added a hydrogen to those to standardize them. Okay, so let's undisplay that column again. Now let's start looking for duplicates. So the first thing I'm going to do is check for duplicate structures. So I click the Find Duplicate. This is defaulted to compound structures. We have several options, but I'm going to just use the default. And you see that it's highlighted 10 rows here. That doesn't necessarily mean there are 10 duplicates, because if there was a triplicate, it would highlight those two. And typically what I do when I get duplicates is I scroll down to the very last set of duplicates, highlight the row below that, and then select everything that's not labeled as duplicate, go up to the View menu, and hide those so that we can just work with the duplicate. So the options here are Hide Selected. Control-Alt-H is a shortcut that I use very often. I also use Control-Shift-H, which will hide the unselected compounds. So this hides the selected compounds, and then it flashes down in the lower right-hand corner. You've got some rows hidden, so it identifies and lets you know that there are hidden molecules or hidden rows in this. So if we look at these first two structures, they're identical. You can just visually look at those. But if you look at the experimental value, it contradicts one. One says it's a hERG blocker, the other doesn't. So if you build a model with this data, the good thing is you're going to be right 50% of the time. The bad thing is you're going to be wrong 50% of the time. And it's probably going to confuse the training algorithm. So these are compounds we would need to remove. I'm going to kind of make this a bit smaller, and we can, since the duplicates are under one another, we can see that this next pair also needs to be removed, and then this pair contradicts, similar to this one, and we can just keep going down looking at these contradictions. So these are compounds we want to delete. So now let's look at this next pair here. So yes for both of these, so we really only have to delete one of those compounds and retain the other. And then similarly, these need to be removed, and we'll remove one of those. So now we end up deleting some of those compounds and cleaning up the data set. Then to bring all the structures back, we can go View, Unhide All. That will bring all of the compounds back into the spreadsheet. Now we've got 662. Now we're going to look at duplicates, and we're going to ignore stereochemistry. So our model looks at 2D descriptors that don't encode chirality. So if there is chirality in there, it will have the same descriptors. So again, I'm going to go down to this bottom pair, bottom set here. Let's see, let's do that one more time. Okay, and then go down to the one that's not highlighted here, and go all the way to the bottom and undisplay those particular fields there. So go into View, Hide, again, Hide Selected. So now we've got the duplicates. Going to shrink this up just a little bit. Now if we look at this, here is a triplicate. So you got duplicate under each other, so that's a triplicate, so we need to pay special attention to that. These first two we need to remove, so on for the second set of pairs and the third set of pairs. So let's delete those, and then let's look a little bit more detail of these. So here we have the hydrogen going back, we've got the hydrogen going forward, and then unspecified. And this one is the conflict, so we need to remove all of those compounds. And then we'll remove one of these, both of these, both of these, both of these, and then one of these, and both of these. Okay. So now we've cleaned up the duplicates. We can go back into unhide all. Okay, so the next thing I'm going to do is kind of interrogate the SAR of this data set. I'm going to use matched molecular pair analysis. And typically in matched molecular pair analysis, it's good for finding activity cliffs, which is essentially what we're doing in this case. Now, you have to be a little bit careful because these are categorized just yes and no. We don't have the raw IC50 data. So two compounds, one could have an IC50 of 9, the other have an IC50 of 11, and they're very similar to each other, and they really do have similar IC50 values, but they're in different categories. So that's going to be hard for the model to predict. But it's nice to know how we'll do on these compounds. Maybe you can highlight these and look at these after you've created the model and see how you do on these. Similarly with all the compounds that I just removed, really the best thing to do is keep those in an external test set and then apply your model to those molecules, because eventually you do want to predict those compounds. And maybe you'll find that there was a multitude of compounds very similar to that were either blockers or non-blockers, and the model should pick that up. Okay, so to go into the matched molecular pair analysis, I can go into the chemistry pull-down menu and click on generate activity cliffs or generate pairs. At the top of this dialog box are the similarity of the two compounds. So with matched molecular pair analysis, we're comparing all the molecules to all the other molecules, and we're trying to find ones that are similar. And similar has to have some kind of criteria. Here the criteria is a maximum number of atoms and bonds between the two pairs can have at most 20 mismatches. The minimum Tanimoto can be 0.65, and then the number of sites can only be 1. So now I'll switch to the hERG blocker as the compound attribute and say that there needs to be a minimum difference of 1. Even though this is a textual attribute, the program can still pick that up. And it tells us if we want to look at these pairs, we go into the pairs table. So let's look at these pairs. So I can blow those up. In this first column is the first compound, second column is the second. So we're comparing these two compounds to each other. This column here represents the hERG blocker experimental value for this, and then the second column is this. So this one is non-blocker, this one's a blocker, and then it also shows the change in this third column. So if we look at these two molecules, it's pretty interesting. There's a plus charge on this nitrogen in the imidazole, then in this compound the plus charge is here. And really all you're doing is flipping this bond back and forth here, and the charge goes from one nitrogen to another. So really that's just a resonance effect, and these are actually duplicates. There is a chirality preference here. So this might be something I need to maybe remove from the data set. Then let's look down at this next pair. So for this compound on the left, the hydroxyl group is highlighted. Now, under the settings, you can change to a bold structure display. So I'm going to change that, and so that can kind of make these appear a little bit bigger. Hopefully you can see those on your video monitor. So here, if you remove a hydroxyl group, then you've dropped the IC50 so that this compound becomes a blocker. For this compound, removing this methyl group makes this compound a hERG blocker. So maybe this is introducing some kind of steric effect. And maybe you can use that if you're trying to, if your compound has a hERG liability, maybe you can add a methyl group close to a protonatable amine, and that will make it sterically interact or prevent it from binding to the hERG channel. If we look at this fourth pair, this is an interesting pair. This compound here, I recognize. For Christmas, someone bought me a coffee mug with an image of caffeine on it. So this is caffeine, and according to this data set, caffeine is a hERG blocker with an IC50 below 10 micromolar. So don't have too much coffee according to this publication. If you have this nitrogen with a methyl group, it's a blocker. If you remove it, it's a non-blocker. And then we get some similar effects down in these compounds. This one, the one on the right, has a bromine introduced, so it's much more hydrophobic. That's part of the pharmacophore for hERG. Then if we look at these pairs, this molecule is the same in both these. Over here, you've just got this tertiary butyl group. Here you've got a hydroxyl group connected, and these are hERG blockers, whereas the ones with the acids are not. So these compounds, all three of these compounds, have a protonatable amine in them, and but if you have an acid group, you've got a Zwitter ion. So Zwitter ions, according to this, may not be are not hERG blockers. So, and then finally, for this last pair, we've added this big hydrophobic group over here with a fluorophenyl, and that is labeled as a non-blocker. So that just shows the match molecular pair analysis. You could take this data set and then take it into ADMET Modeler and create a model for these compounds. I'm just going to go through the slides for that. So we've redefined the interface for ADMET Modeler also. So initially you would just click on the ADMET Modeler icon. You would select your dependent variable. In this case, it would be hERG blockers. The next thing you do is define the descriptors, potential descriptors for the model building process. Next, you specify your training algorithm. We still have the same training algorithms that were in ADMET Predictor 7.2, so artificial neural network ensembles, support vector machines, KPLS and MLR. Then you set up your training algorithm parameters. Next brings up a dialog box with a summary of the model building steps. So you can kind of check what you've specified in these previous steps. If something is incorrect, you can go back and through these and correct them. And then finally you would create the models and then select the best model, export it, and save it for future use. Okay, so now let's go on to the next section. This is on BACE1 inhibitors, so I'm just going to bring up some examples. BACE1 is a target for Alzheimer's disease. BACE1 stands for beta secretase 1. It is an enzyme in your brain that cleaves an amyloid precursor, and this is what causes some of the problems in Alzheimer's. It produces a soluble peptide C99, which is the rate-limiting step in amyloid beta formation. And so there are various companies that have developed inhibitors and put them in to clinical trials. And very recently, I'd say in the last few months, Merck has submitted another compound for Alzheimer's disease that is a BACE1 inhibitor, and it's similar to some of the molecules I'll discuss in that it has an amidine functionality here. BACE1 contains 2-aspartic acid residues in the active site where the inhibitors can interact. So this is an example of one of the inhibitors from a recent Janssen paper. So this is the amidine functionality here. It will protonate, and then since it's a positive charge, it can form salt bridges with the carboxylic acids and also hydrogen bond donor acceptor pairs. So I made this image with a program called Yacera View. Here's the website here. It's a nice program for visualizing proteins. So let's go back into ADMET Predictor again. So again, I'll double click on the ADMET Predictor icon, and then I'm going to open up a set of BACE1 inhibitors. So these are compounds that I downloaded from the Chemical database. Let's change this setting so that it's not a bold structure. So there are many fields downloaded. I initially took that into Excel, and one of the things I did was kind of concatenated the reference together. In Chemical, it's the journal, the year, etc. And I just concatenated that into one field and then identified that or added that to the input file. For some papers I could get, I defined a link. So I downloaded the PDB file, and then I created a link to that in the spreadsheet. So if you put a file : / that means it's a local file on your computer, and then you point to the file. So that's a nice way to organize your spreadsheet so that if you have questions about the publication, you can bring it up. Also, there's a compound key, so if you notice, this is compound key 62, and that was the first molecule I brought up. Another thing I did was submit these SMILE strings to a website that will convert a SMILE string into a SD file, and then on my computer I defined SD files such that I double click on them. It'll bring up this free program called JMOL, which I've used quite a bit in the past, and so you can get a look at the 3D coordinates of the molecule and link them in your ADMET Predictor spreadsheet. Similarly, some of the compounds have crystal structures. So I've linked that so that if I double click on my computer, a PDB file, it will bring up Yacera view. It's a nice program. I can push F7 and it renders the protein very nicely in this cartoon. You see the beta sheets and the alpha helices, and then you can modify the molecule a little bit, and so get an idea of how that's binding in the pocket. Okay, so now let's open up a subset of this data and try and generate some classes. So I'm going to open up a subset of 884 inhibitors. The original data set from Chemical had close to 7,000 compounds, and since the mode of action of this enzyme is to cleave a protein, a lot of the early drug discovery used peptides to bind to the pocket, and those just could never be developed into drugs. But those were in the Chemical database, and I just removed all of those compounds from there. So let me bring up my cheat sheet here. So let's start with this, and the first thing I'm going to do is point to the fields that were imported. One is the IC50 extracted from Chemical, and then I added a column of PIC50 values. So under data and add attributes, you can add an equation, and then you simply define that equation in the interface. So I added that. So the first thing I'm going to do is create a heat map of all of these, click OK, and then again I'm going to sort these. So this is the most potent compound in the database. It's 200 picomolar, so very active compound, and since red means stop, I want to reverse this direction again. So set it in the descending order. So now the most active compounds are green. This field, goes the opposite direction, so it's okay there. So I'm going to go into the chemistry and generate classes. So I click here. We can also go down to the classes tab and bring up the same dialog box. So the default here is the frameworks method. This simply identifies frameworks within the compounds. And if I'm in the compounds tab, it simply adds a column specifying what class every molecule is. And then I can use these tools up here to go through the various classes. So this is the first class. There's 63 compounds in it. It's highlighted the scaffold in blue here, and then I can go through to the next one. So this just is a singleton class. etc. So you can traverse through the various classes here. This green symbol here will bring back all 884 compounds with their structure highlighted. So it was before, kind of like before I clicked this first button. We can also click the red one, and that just unhighlights everything. If we go into the Classes tab, it will show the classes generated. Let's pay particular attention to this distribution plot, and we can modify that and specify that we want that to show the PIC 50 values for these. We can sort on the class size in descending order, and so we have the various classes highlighted over here in the structure. This has 63 compounds. This is the distribution of PIC 50 values. This next class has some more active compounds in there, so it's a little bit more active. Let's focus on this class. This looks like an interesting class, and what I'm going to do just for this demo is just do a substructure query for this class and then delete the rest of the molecules. So the first thing I'm going to do is copy this as a SMILE string, go back into the Compounds tab, and then go under Edit Query, take that into MedChem Designer, and paste the structure I just had into here. Now I want to remove the phenyl group, so I just want this scaffold here. I bring that back into here, click OK. It's highlighted 195 compounds. I can invert that selection. I use Control-I as a shortcut. So it's selected all of the compounds that weren't selected, and then I'm just going to go in here and delete those compounds and just have the 195 remaining compounds within here. So you see that it's highlighted these fields. Now I'm going to go into the Classes tab and use this to just put all these into a SQL superclass. You'll note that this is highlighted in red. That's from the query I just performed. I'm going to turn off that query highlighting. And then I'm going to right-click, and I'm going to generate a maximum common substructure for this. And so it generates this image in blue here, and has defined that in all these compounds. And what I want to do is first align these molecules together. Now, I prefer, when I've been looking at these BACE inhibitors, to have this amino group over on the left-hand side. That's kind of the standard format I see these. So I'll move that over into MedChem Designer and just move this down just a little bit over here. And then I'm going to go into the structure and flip that horizontal. So now that group goes over here. And I also want to clean this up a little bit. So this carbonyl is not very nice. It should be 120-degree angles. So I'm going to clean that up a little bit, move this phenyl group out, select the oxygen, and clean it up. And then similarly, I can select the phenyl group and clean that up. So that looks good. And then I'll take that over back into ADMET Predictor. Now I can right-click on these and align all these compounds together. If I go back into the Compounds tab now, we have all of these compounds aligned very nicely. Okay, so now I'm going to go into the Classes tab and generate an R table for this. So it's defined these two substituents as R1 and R2. There are some compounds that don't have a methyl group here, so that's the R3 group here. And then I'm going to take this into the R tables tab. So it displays the scaffold up here. This pane is dockable, and then you have the various R groups, so it creates a unique column for each one of the R groups. And again, I'll expand these a little bit so that you can see the compounds a little bit better. And then I'm going to just sort on these. So you can sort in ascending order. You can also sort in descending order. And if you look at these two compounds here, these have kind of a bicyclic group in here, a spiral group. And those really don't fit my pharmacophore. So I'm going to go back and delete these compounds. So if I go back into the Compounds tab, and then perform a query on this. again, take this into MedChem Designer. So let's center that. So there's new options in MedChem Designer to specify kind of Marcouche atom types. I'm going to right-click on this. Highlight this atom, right-click on it, and set the ring bond count to 2. So all the molecules that I want have a ring bond count of 2. The ones that I don't have a ring bond count of 4. So when I highlight that, it shows all except the highlighted everything except for the spiral compounds. I'm going to invert those and then take those up to the top. So you can see those here, and then just delete those compounds. So now go back into the Classes tab again, clear the structural highlighting, redefine the R tables, and that'll bring us into here. Now, if I go back into the R tables, it shows them here. I can bring down the R group analyzer, and this is a nice way to analyze the R group. So if you see, for each one of the R groups, it's created a new tab and shows the unique R1 groups in this case for this tab. You see a lot of them are singletons, but for the cyclohexyl group, there's 8 compounds here, and we see the distribution of activities, and there's not much of a change for these 8 compounds. You can double click on here and it brings up this dialog box, and then you can kind of go through each one of these compounds in this set, and you'll see what's varying is this R group up here. So that's a nice way to interrogate those molecules. Similarly for the R2, R3, we can bring up the matrix showing the R1s as rows and the R2s as columns. We can change those R1, R3, or R2, R3 so that we can show all the pairs. When you have, and then I'm also going to change, instead of nanomolar or IC50s, I'm going to change to the PIC50 values. And when you have something like this where it's kind of a pie chart, what's happening are these are the ones, the 8 compounds where that R group is varying. You've still got cyclohexyl and phenyl, but the R3 position is varying in this. We've got another view that is R1 by R1, and with this view you can see that if you change a phenyl into a pyridyl, you can look at that pair and how the activity changes here, and I think it increases for this particular compound. Then just finally I want to show R group explode products. So in this case it takes your scaffold and puts all of the R groups into this table here, and what the R group explosion will do is take every R2 and match it with every R1 and R3 in a combinatorial fashion so that you create that full matrix of compounds out there. Now, I'm not particularly interested in variability in the R3 group, so I'm going to highlight those R groups in this table and disable those. So you'll notice that the estimated number of products drops. I'm going to then display those in a new window, so I click OK. It explodes that, and then we'll bring that up in a new instance of ADMET Predictor. So that kind of concludes the demonstration of analyzing the R tables and exploding those properties. And then finally, I'm just in this last section, I'm going to briefly discuss kind of an early lead discovery project. So let's say you're investigating a new target. There are no known modulators, but there's a hit from a single related protein. So you would just take, start with that structure, let's say, and this is just a random compound I extracted from the Kimball database. You see it's got a urea functionality and then kind of an ether type linkage here. So if you're a med chemist, the first thing you might want to do is take this into MedChem Designer, calculate ADMET properties for that particular compound, look at the ADMET risk values, and then just maybe copy that molecule 5 times if I've done here, and then make modifications to that and calculate different ADMET properties. And then you can take this back, maybe these are synthetic candidates, take those back into ADMET Predictor and save those in a database. You also might want to take your compound and search an off-the-shelf database of compounds. For example, I've got the zinc database defined here, so you can perform similarity searching on this molecule. We also have a tool in ADMET Predictor called combinatorial transforms, which makes point mutations and other transformations of the molecules. And it was built in collaboration with medicinal chemists, so there's going to be some overlap, hopefully, between these combinatorial results and some of your own ideas. Hopefully, it'll generate some ideas that you hadn't thought of through the combinatorial transforms. And again, you can save those as ideas, synthetic candidates, and then rank those. Then finally, you can also easily create virtual libraries in ADMET Predictor 8. So here I'm going to show just an example of a tetrahydroisoquinoline. And so what I was thinking about with this lead molecule is that if you close this ring up here and then convert that to a phenyl ring, then you have your tetrahydroisoquinoline. You can react an isocyanate or isocyanate with amines to form your urea. So that might be a good way to resynthesize a very similar hit to this with a slight modification on it. So when you create a reaction in ADMET Predictor, the first thing to do is kind of think about what reagents you're going to use in them. I've done a Pictet-Spangler reaction here. So you need phenethylamines. And these need to have a hydrogen ortho to the ethylamine group here. Now, if you have a case like this, where it's non-symmetric around this bond, it could react here or here. The program will produce both those. Experimentally, you might want to avoid that. Maybe a med chemist would, know how to specify that. If you have a fluorine here, that's okay. Heterocycles might be okay. So you could define these reaction groups and then use the interface to enumerate that particular library and then search in that. So that concludes the slides and the demonstrations. I just want to conclude by saying that we still have the top-rated QSPR models for accurate prediction of ADMET properties. We've added a lot of property visualization tools for easier pattern recognition. These include star plots, heat maps, scatter and distribution plots. We can intuitively create classes, R-table generation, analysis. I need to mention, though, that this is an extra module called AP_MedChem Studio. So that's an additional license feature. It will allow you to do library searching, combinatorial transfer, form, etc. And then the data curation, is going to be standard now in ADMET Predictor 8. So anybody that has a single license module can license or have access to those. So finally, I want to say that we offer free 3-week evaluations of the program. We have flexible licensing options, and if you want to contact me, here are my contact details. I'm also working on putting up videos of each one of the demonstrations I did today on our website, so that'll be accessible along with the video of this webinar. So I thank you for attending, and we'll go back to Bob and see if there's any questions.
Hi, this is Bob Clark. We've got 2 questions at the moment. The first is from Jonathan Chong. What is the quick way to create the class list in the BACE1 talk?
Just click on the let's see, so I'll open that up again. Oh, it's already open. I'll go back to the Compounds tab. It's simply clicking on this icon here, Generate Classes. So here we'll create ring anchored systems, and then just click OK, and that will add the column, and then we can interrogate all the compounds in each one of the classes here. So that's the quickest way, I would say, is just hitting that icon. Does that make sense, Bob?
No, it works for me.
Okay.
I think that's what was being asked.
Okay.
The next question is actually several questions, one of which I think we're probably not going to be able to get to in the talk, but and I apologize if I mangle anybody's name, but this is from Grigory Garetsov, I believe. How easy is it to import other data, for instance, in-house solubility or pKa predictions from some in-house model?
So yeah.
How easy is it to import other data?
Oh, very easy. So you would just have a text field that would contain the compound identifier. So this is what it's going to try and match up your text file with the structures in the data set. So your text file doesn't have to contain all of the structures in your data set or all the rows in your data set. It contains a subset. They don't have to be in the same order or anything like that. And then you would just go under File, Import, Compound Attributes, browse to the text file, and then you'd get in a subsequent dialog box, it would show all the fields in that text file, and you could specify which fields to import if you don't want to import them all. You can also specify whether it's going to, the data is a real number, an integer, or a text field. So it's very straightforward and just matches the compound identifier to the one in your text field. And it's very robust. It can handle non-standard characters nicely, and I've never had any problem importing data. So it's very quick and easy. And then once you get it in there, you can save that. You could also create a library or a database with just that data, and we'll include that text data, and you could also do searching on that.
Okay, another question, and another part of that question, which we'll touch on now, has to do with whether those imported properties can be used, for example, in ADMET Modeler.
Sure. Okay. So if you have descriptors that you've calculated outside of ADMET Predictor, you could import them. You could have those included in the SMILES or SDF file that you read in, and then once you go through the interface. So in this, let me back up a little bit. So in this dialog box here, on the left side will appear your imported descriptors. You would just highlight that and then click a button to move them over to the right side here, and then they'd be available for model building. So and then within the process of model building, some of those descriptors may be used and others not used. So it's again very easy to import your own descriptors and use those to build your models within ADMET Predictor.
Okay. A question from Julien Gressel are there any details about gastrointestinal tract absorption, for example, absorption in the duodenum, so forth, in order to use it in GastroPlus?
Well, GastroPlus has a module called the ADMET Predictor module, and with that, when you import a structure into GastroPlus, it will calculate things like solubility, permeability, diffusion coefficient, etc. with ADMET Predictor, and then you can use those predictions to perform PBPK model simulations, etc. And it'll also import the clearance data from the SIP model. So that's incorporated into GastroPlus, so you can use those in there. Within ADMET Predictor, you can look at things like absorption risk, which examines kind of the physical chemical properties of the molecules, and issues liabilities or scores the liabilities. For example, if you've got a low solubility compound, it would flag that with the absorption risk and the ADMET risks.
There is a model in there for effective jejunal permeability, which is actually one of the parameters that gets imported into GastroPlus.
Yes, yes.
That happens to be one of my babies. So. There's a question from Safaraz Alam of why does the software not calculate pKa values for some of the compounds?
Hi, Safaraz. I've been collaborating or exchanging emails. They won't have, if they don't have a protonatable amine or a protonatable group in them. So maybe some of the solubility data files. Let's just open that up again. Calculate the ADMET properties. And then look in the PhysChem Bio. So let's look. Okay, so this compound here doesn't have any acidic groups or protonatable groups, so there's no pKa calculated for that. So that would be the only reason. We calculate all of the microstates for the molecule, and that's something that other software doesn't do, and that's also something that you can't get out of an experiment at times. So the experiments only have a certain pH range that they'll predict the pKa's of. So that's a big advantage of using our pKa prediction tool within ADMET Predictor.
And Sarfaraz also had a question about what functionality required in a modeler license.
It's just so it is a license. If I look at my license status, so ADMET module AP modeler, this one here is simply a license, and that allows you to create different types of models, classification and regression models. It uses different. You can use different training algorithms to develop the models, and then once you've created a model, you can save that model and then use it to in the future to predict any compounds.
Rochelle Beanstalk had a question about whether there's a reference publication regarding the algorithm for determining the classes. Do you want me to answer that one?
Yes. Okay.
Because I'm sort of responsible for everything that hasn't been published. The roots of the algorithm go back to BioReason days. We acquired the program and actually the programmer from BioReason when they went out of business. It's an extremely complex algorithm. The key point is that it operates entirely off substructure overlaps. And it's just a question of how you prioritize the overlaps. And there are features you can control that determine how homogeneous you want the classes to be. So the short answer is there is a publication which we will send you the reference to, which roughly describes it, and we do describe it in our manuals, but it is not a full description of the algorithm. Basically, because that would be several thousand lines of computer code.
Very good.
And let's see. Oh, and Rochelle said thanks, so I guess that was an adequate response.
And
the frameworks part is based on the Bemis and Merco publication. That is described. sorry about that. The ring anchor system and chain anchor systems is what I was referring to. The frameworks is the Bemis and Mirko methodology. And the last thing has to do with the R tables. Again, this is from Grigori. He wanted to know how the R groups are sorted by molecular weight or alphabetically based on the smiles or what?
They're by the molecular weight of the R group.
Yeah, and you can change that interactively as well. Change how they're sorted. And what is the algorithm behind the matched molecular pairs feature? It actually keys off the same infrastructure plus some literature work, I believe, that is used for the class generation, not the Mirko based, but the in-house class generations, and it's based on fast shared molecular substructures.
Yeah, so it's one of the keys there is it's based on the maximum common substructure rather than the 2D fingerprint. So it's a little bit more intuitive, I think, because it matches up the fragments and aligns the fragments together very nicely, as you saw in the demonstration.
And I think that covers most of the questions that it's practical to respond to. Covers almost all the questions. And the ones we don't, we will get back to you individually. And with that, I'd like to thank Michael for an excellent webinar to underscore the fact that we're always happy to have people evaluate the software. And with that, I think we can thank everybody and adjourn.
Thank you very much, everyone, and I'll see you next time. Bye-bye.
Bye-bye.